Hi everybody, and welcome back to Digital VLSI Design. I'm Dr. Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll be going over Lecture 11, Chip Finishing and Sign-Off. Our lecture today has two parts, Sign-Off Timing and Chip Finishing and Sign-Off. We'll start with the first part, Sign-Off Timing or Advanced Concepts in Static Timing Analysis. So, do you remember those pesky timing margins that we mentioned in the lecture about static timing analysis? Well, if we look at the max delay and the min delay formulas, we added this plus delta margin here to the data path and minus delta margin here to the data path. It was some extra margin that we just added or subtracted to make our life harder. And we discussed skew and jitter. In fact, skew we added here to these formulas, and jitter we also showed how it can be added or subtracted from our formulas. But is that all there is? Well, if it was, there's a good chance that all the CAD engineers could retire. There's a lot more. So what, why, and how do we apply these additional timing margins that I actually lumped into this delta margin type of a parameter? So let's start with the basic kind of approach, which is known as BCWC, or best case, worst case timing. So this is the straightforward and traditional way to run STA. So max delay setup checks are run on the worst case conditions. Those are the slow conditions. Often we take something like SS for the process, right? And we take a low voltage, so something like 0.9 of VDD. And we'll take a worst case temperature, which in the past was something like 125 degrees Celsius. But since we have temperature inversion now, it can be a low temperature, such as 0 degrees or minus 40. Min delay checks or hold checks we run on best case fast conditions. So we take something like FF, okay, we'll take 1.1 of VDD, and we'll take in traditionally 0 degrees or minus 40 degrees, depending on what spec we want to meet. And nowadays, again, with temperature inversion, it'll be the higher temperatures, 85 or 125 degrees. And the way to do it, actually, in a Cadence common UI tool, would be to set this dB parameter timing analysis type, best case, worst case. But that doesn't take into account all kinds of variation that can occur across the chip. For example, we can have a temperature variance that can be really different at different areas of the chip, areas that are just kind of asleep or areas that are close to like a high working processor or something. So that brings us to the concept of on-chip variation, or OCV. So on-chip variation is a spatial variation. Chips are big and delay elements can be far from each other. Process voltage and temperature variation can affect different parts of the timing path in opposite directions. So we all know what process voltage and temperature, or PVT, variation is from this course and from previous courses. And we see that it can affect different gates on the whole chip differently. As back-end designers, as chip designers, we always have to go for a worst possible case, be very pessimistic. So we'll assume that really the worst case conditions can occur. So how do we do this? We do it with something called derating. We use this set timing derate command, and what it does, it actually takes the launch or data path, which in a setup would be this, and the problem is that this data path can be slow. So let's make it extra slow by adding some sort of a constant type of a derate. So we'll actually multiply each of the timing elements here, each of the delays here, by some sort of factor. In this case, add an extra 20%. And for the capture path, which we call early, that's the early path, we'll actually speed it up. So we'll speed it up by 10%. So we'll multiply this by 0.9. Now, these will be actually provided by your foundry to show what is a good type of on-chip variation to add. Okay, for hold, we'll do the opposite. So in this case, we want to make sure that the data path is actually slower than the capture path. The launch path is slower than the capture path. So in this case, we'll make this path faster. So we'll multiply it by 0.9 in this set timing derate, and this one we'll multiply by 1.2. Okay, Cadence has some different approaches here than Synopsys, so you got to read the manual quite well and see what actually happens in the tool that you're using. Well, that is a kind of an ultra pessimism. So it's kind of a common practice in VLSI implementation, being over pessimistic. And it's a good practice, because if you're optimistic, you may get a chip back that won't work, or it may be in the field and somebody will send it back to you because it won't work. And if you over design, you know that your yield will go up, and then you'll sell more of those chips that you actually manufactured. However, it's also very painful. The time to market increases because it comes harder to meet your different constraints if you're over pessimistic, and you're also going to hurt your performance. In fact, all of the parameters are worse. Size, power, performance. If we over constrain, we're going to be using bigger buffers, which are going to take more chip area. They're going to use more power, and we're also just going to plan for a lower performance than we probably could have met if we were actually designing for what we could meet and not an over pessimistic case. So we have to ask if the defined OCV methodology can actually occur. In some cases, we'll choose one library for data and another for the clock. That is one of the methods that's done, and it doesn't really make sense. And also, you can sometimes add derating on top of that, or just this derating. It's some sort of a factor that you're going to be multiplying actually the delay of certain cells that could be right next to each other, assuming that they have very different temperatures or different types of on-chip voltage or process variation. So that's really an over pessimistic case, and it was always hard to reach for designers when they were applying this, from something like 130 nanometers down to around 65, I would say. So let's go and try to recover some of our pessimism. And that would be done starting with something called clock reconvergence pessimism removal, or CRPR, or it can also be called CPPR depending on the tool you're using. Okay, so when we want to limit the pessimism, we'll use this CRPR, and it actually removes the derating from the clock path that's shared by both the launch and capture path. So one of the things that was kind of strange, or I would say ridiculous, that was done is that we would put this derating, so on the launch path that was going over here, we were going to, let's say in a setup corner, we were going to slow this down, and then we were speeding this up. But as you can see here in the picture, U1 and U2 are buffers that are on the clock tree. They're part of a common clock path. So U1 and U2 are the same exact buffers, and the wires that go between them, they're shared by both the launch and the capture path. And we were actually derating this, so assuming that U1 was slower by 20% or whatever, and then for the capture path it was faster, but it was actually the same buffer. It might even be in a hold case even the same cycle, and if not, it was in adjacent cycles. So that is an over pessimistic. So you really should go and remove this pessimism, and the tools will actually look for these common points and just remove the derating that we added there. And in our cadence tool, we do this by setDB, timing analysis, CPPR both, and that will remove both for hold and setup this clock reconvergence pessimism. But that's not enough. Still, it was hard to meet these OCV type of definitions, so advanced OCV variation was invented. So the derates were really tough, and the question is, do all the paths really derate the same? Should we just go and take that 1.2 and 0.9 or some other derating factor and apply it to all the cells that we have and all the paths that we have? And the answer is no. Really, variation is very statistical, and what we should be doing is figuring out how the paths behave in a statistical way, but it's really hard to compute statistics. Statistical behavior is really tough. It's compute intensive. So we have to do something easier, and someone noticed or figured out that there are a couple of things that really affect the worst case conditions. So the first one is kind of obvious. It's distance. If you have a bunch of cells that are very far away from each other, then there's a good chance maybe that they'll have extreme temperatures. But if they're close together, that's probably not going to happen. And the same for IR drop or whatever that's going to cause voltage differences and process variations. I mean, a lot of things are local and they're really random between each other, but some of them are local to the area of the chip. And if the cells on the path are close together, there's no reason to add this derate for them. The other one, which is a more interesting case, is the depth of the path. So these variations, especially these local random variations, they're going to be random. They're going to be totally random, and if we have like the VT of two transistors, and there's much less of a chance that two transistors that are adjacent to each other are going to both get this worst case random variation. Usually we're going to get something in the middle. So the deeper that a path is, which you can actually see here, that you're going to actually need less derate because the random variations are going to kind of cancel each other out. So AOCV, or Advanced On-Chip Variation, are libraries that were developed that take into these two things. The distance between the gates on the path. You actually put a bounding box around the path, around all the gates in the path, and then there's a derating factor that depends on the size of this bounding box. And each of the library cells actually has a lookup table that tells you how much to derate by how deep the path is. Now, this is very complex and so forth, and you have to look into it. You have to provide new libraries, but this was very commonly done up until around 28 nanometers or so. So how do you do it? You have to, in your MMMC file, you have to use something like update library set, or when you're creating the library set, add minus AOCV and give these special libraries that are AOCV libraries. Again, they're new libraries. They need special characterization and so forth. And the other thing is, when you do the timing analysis type, you have to do setDB timing analysis AOCV true. There are many other parameters, of course, and you should refer to your manual to exactly how to set it up. But this is the basic thing. But again, that wasn't enough, and that's why we got to POCV, or parametric on-chip variation. So AOCV is really cool. It does reduce a lot of the pessimism, but it's still not accurate, and it's still very pessimistic. And remember, the variation is statistical, and it's really different for each gate. And what AOCV is doing is actually counting the number of cells there are on a path, and it's not really relating to each gate how different it is from each other. The real way to figure out what type of pessimism we should put on here is by running Monte Carlo simulations on every path. We should take our paths, we should simulate them in SPICE, run Monte Carlo simulations for how the different gates could come out, and then figure out what our 3 sigma or whatever distribution should be for a worst case. And that's known as statistical STA, or SSTA, and it's a concept that's well known and has been researched quite often, but it's really computationally intensive and it's not used very often. We need something easier and faster and so forth. So we have to be more realistic, and what is done is this POCV, or also sometimes called statistical OCV, SOCV, that's the cadence name, this is the synopsis name. They also give a different library format for this. And what it does is it provides distribution for each gate in the library, so each gate gets its mu and its sigma, and then we can calculate the delay according to the gates on the path. And this also, again, has a new type of a library format. It's either called LVF, Liberty Variation Format, or SOCV for the cadence tools. They're very similar to each other, and again, you have to get these, and it's very suggested to use under 16 nanometers or so. So you would again use this with some sort of setDBs, such as setDB timing analysis SOCV true, and there are a lot of nooks and crannies that you have to go into and look and fine tune when you set this up. But really, when you go back down into sign-off timing, you should nowadays, in the state-of-the-art type of scaled processes, you should use these POCV or these SOCV libraries and timing to reduce a lot of that pessimism that we took with standard OCV. So just another point, which is kind of independent of those different modeling tools, there's something called path-based versus graph-based analysis. So something we didn't discuss before, but when we discussed our STA, we gave types of algorithms that went and found the rat and the at to each node on the path. What is actually used in STA is usually something called graph-based analysis, or GBA, but it provides a lot of pessimism. It takes a worst case, and what we should do during sign-off to remove that pessimism is use what is called PBA, or path-based analysis. And let's see what the difference is. There's a kind of a nice picture here from VLSI Expert, and you can see in the graph here we have just some sort of a timing path, and we have these two AND gates, and the AND gates each have two inputs. And if you look, we have arcs in here, and the arcs can go from like 0.5 nanoseconds to 1.5 nanosecond from A to out, and 0.2 nanoseconds to 1.2 nanoseconds from B to out. What is done in graph-based analysis, which is what is used basically in all the timing tools up until the sign-off level, what we do is we just merge this. We don't want to deal with all these different arcs that can be falling arcs, rising arcs, and so forth, and several inputs through the things. So what we do is we just merge this. We look for the worst case. The fastest arc is 0.2 nanoseconds. The slowest arc is 1.5 nanoseconds. So we provide a graph like this, where we would just turn that gate into 0.2 to 1.5 nanoseconds, and that's done for all the gate, and it gives us a big speed up from what should actually be done, which is path-based analysis. In path-based analysis, we actually draw the real arcs that come through, and then we have to check the timing through each and every single one of these possible arcs. And really the problem is that it takes about 10 times longer to run it. It's an order of magnitude longer to run these path-based analysis checks, but it really, when we use the graph-based, it adds a lot of pessimism. So during sign-off, we really should do that. You can use the graph-based for different types of optimization, and then just when you're doing sign-off, make sure that everything meets, and maybe you even fixed a bit too much if you use the graph-based analysis. So use PBA for your sign-off. So another point is RC extraction. What do we do with the metal layers? What do we do with the back end? We've always discussed kind of what happens with process variation with the front end layers, with the transistors themselves. We have fast corners, we have slow corners, etc. But what about the back end layers? They also have variation. And usually how we do this is we provide several extraction options to the extraction tools. So for example, if we look at the picture over here, we have these two metal layers that were drawn over here. This is one and this is the other, and there's a dielectric in between them, and that provides us some sort of a coupling capacitance between them. But actually, they came out differently. And this could be a side-to-side or a top-to-bottom type of a drawing, but you can see here that the capacitance is much higher in these areas because we had this widening of the wire, and the wires got closer to each other. This would be called a C-worst type of a corner, versus if the wires were thinner, then we would have a bigger distance between them and the capacitance would be lower. So this is what we would call a C-best type of a capacitance. So C-worst is a minimum metal spacing, tall wires, max surface area, versus C-best is a max metal spacing, short wires, and minimum surface area. We can see kind of a schematic of this over here. So in C-worst, we would have these very, very big wires, and the big wires would be close together. They'd have a lot of surface area that was adjusted to each other. And the same thing with top and bottom. We'd have the wide wires would have much more area and they'd be closer to each other. And that versus a C-best where they're farther away from each other, they're shorter. Over here, they're not as wide, and the distance between two layers is bigger. So those are two options that you can put into the extraction tool. Like for example, with Cadence, it would be with the QRC tech file, and that will give you a C-worst and a C-best extraction. But that doesn't take into account the resistance, and the resistance actually it acts differently and sometimes contradictory to the capacitance, and that makes things all the more confusing. So if we have these two wires that we have here, obviously if the wires get wider, as you can see over here, we have a wider wire, that's more room to have current flow, and so we get a best case resistance, versus if our wires thin out, we have a worst case resistance and we'll have more resistance over here. So what happens is we want to have some sort of combination between the resistance and the capacitance, and then the thing is that we have the opposite thing. When the capacitance gets worse, the resistance gets better, and the opposite. So how do you make this RC worst or RC best? You can see a kind of a schematic of how it's done over here on the slide. So how does this affect the RC values? So for C worst, we get the maximum capacitance and we get the minimum resistance, and for C best, we get the minimum capacitance, and that also gives us the maximum resistance. For the RC worst and RC best, which are kind of a combination of the two, RC worst gives us the maximum resistance and RC best gives us the minimum resistance. So then we can take for the wide wires, we'll have a maximum capacitance as well, but for the narrow wires, a minimum capacitance, and the opposite for the RC best. You can kind of see it plotted out on this type of a space graph over here. Okay, what do we do? What do we do for our delay calculation? We have to choose one of these extraction corners to use with each of our process corners. So one thing that you could do is you could use only the capacitance. The capacitance is the only thing that affects the cell delay. Remember, we have our type of a standard cell gate, and it has some sort of an on resistance, and whatever we have in the load is, and despite the fact that this is a distributed, type of a resistance over here, and whatever it is, this on resistance, it actually sees this is a whole lumped capacitance. So we could only look at the capacitance and not care about the resistance. But when we have long wires where the wire delay is significant, then actually we should take an RC best or an RC worst type of a extraction. So there's no right answer here. There's methodology. Maybe you should try it with a few different extractions options if you can spare the computation time. Another thing that can affect our timing is aging. So in modern VLSI design, aging, or the time that we use, the reliability over time of our chips, is a big deal. So device characteristics change over time, and hot carrier injection, hot electrons, is something that happens often, and that changes the VT of the transistor. We also have other effects such as negative bias temperature instability, NBTI. We have time-dependent dielectric breakdown, and of course we have electromigration, which we've discussed before. All of these really change the device characteristics. So how do we deal with it? Well, one of the things is methodologically, if you can use a lower VDD, which is a trend that's been going on for the past few years, it's better because we'll have smaller fields. Smaller fields cause less aging in general. But that's one way to do it, and it's not enough. And it's not sufficient because usually we're using some nominal VDD, which might be too high to really cloak those aging effects. So one thing that we could do is just add some more timing margins. So remember, our delta margins give some sort of a lumped factor into it, and we can become even more pessimistic. But something that's very common to do is actually use aged library models. So we can take aged models of the transistors and characterize them for a certain type of aging. Let's say if we have we assume what the chip is going to work after 2 years, we can provide libraries that are aged 2 years and see how our chip's going to work, see if it still works, see if it still meets usually our our setup is the more significant problem in this case, because things tend to get slower, not faster. Another thing that's common to do is adding aging sensors, and if we add aging sensors, we can adjust the frequency and voltage to compensate over this, and this is something that's commonly done in more complex systems today. There are even different types of companies such as Protein Techs, which checks the aging around the chip and will actually try to provide information to the operating system to tell that things are going to break down soon. So that brings us to a general time sign-off type of a timing flow that we have in a cadence tool such as Tempest. So we usually use this time design command. The time design command is a super command that runs many different report timing type of commands. If we use the minus sign-off option, what it's going to do, it's going to actually call the QRC extraction tool, the very accurate extraction tool, and then run our timing reports, and it will also provide all kinds of options such as we saw before, maybe path-based analysis, maybe using parametric AOCV and so forth. When we have finished our sign-off timing, what we're often going to do is use an external timing tool. So we're going to export our design to the sign-off extraction tool. We're going to output a netlist and a GDS. We can use, for example, the top tool in the field, which may not be the tool that's integrated into our sign-off. So we take out the netlist and GDS. We load this into we extract it, and we usually get a file that's called a SPEF file, which has the information about our timing extraction, about our RCs, and then we can read that extraction into our timing tool, such as read SPEF or whatever corner we want to do it in. Then we can run our static timing analysis in the sign-off tool. Using the sign-off tool, we can do all kinds of things. We can provide an SDF. SDF is a standard delay format that shows what the delays of the different gates and so forth and wires are, and we can use that to run ECOs, fix hold, and fix setup according to our sign-off timing. The tools can usually also provide a script that will tell where to put buffers, where to change things and so forth, where to upsize different types of cells to try and fix the timing problems, and then we would run this in a loop kind of until we would meet all our sign-off timing constraints. Another thing that we could do is we could take that SDF and punch it back into our simulation tool and run sort of a dynamic timing analysis or gate level simulations with actual delays to see that things are working and give us sanity check. We can't do it on everything obviously exhaustively, but we can use some simple test benches to check that things look like they're working right. So that was our part one of our lecture about sign-off timing, and now we'll move on to chip finishing and sign-off.